In this video, we're going to talk about free energy and its relationship to entropy. So we've been talking about the idea of spontaneity. In the previous video, we described spontaneity based on microstates. And then we used this idea related to entropy. We said the universe tends toward disorder, toward an increase in entropy. And if we can define the entropy of the universe, so delta S of the universe, as our delta S of the system plus our delta S of the surroundings, and remember S is our entropy, so the entropy change of the system plus the entropy change of the surroundings will give us the entropy change of the universe. And if we can determine the entropy change of the universe, we can determine whether a reaction is spontaneous or not. So if we have delta S of the universe greater than 0, then we have a spontaneous reaction. So this requires us to find the entropy change of the system as well as the surroundings. Now, we talked about finding delta S of the surroundings previously by relating it to delta H of the system at a certain temperature. So if we then put this together with our delta S of the system, so delta S of the system plus our negative delta H of the system divided by T. Okay, so incorporating those two elements together into the same equation, I'm now going to multiply both sides by T. So we have T times delta S of the universe equals T times delta S of the system minus delta H. Alright, and the T's would cross out here under the delta H. Alright, one more thing I'm going to do. I'm going to multiply the entire equation, both sides, by -1 to try to get this into a certain arrangement that we will see in just a minute. So negative T times delta S of the universe is now equal to delta H of the system minus T times delta S of the system. This part right here is called delta G, or the Gibbs free energy. Alright, so I'm going to rewrite it. Delta G for a reaction is equal to delta H of the system minus T times delta S of the system. And this one equation can determine spontaneity. Now notice the relationship between our delta G and our delta S of the universe now. Because delta S of the universe being positive gave us a spontaneous reaction, now because of this negative sign, delta G would be negative for a spontaneous reaction. So delta G is less than 0 for a spontaneous reaction. Delta G would be greater than 0 for a non-spontaneous reaction. Alright, and that leads us to the most important equation for what we're going to talk about in this part, the Gibbs free energy equation. So this is the equation that we just derived based on our delta S of the universe. So our delta G determines spontaneity for a reaction. Delta H is still our measure of enthalpy, or the heat for our reaction, and delta S is still a measure of our entropy, or our chaos for the reaction. And then T is our measure of temperature at which the reaction takes place, and this must be in Kelvin. Alright, so if we have a negative delta G, the reaction is spontaneous, and that relates to a positive delta S of the universe. If we have a positive delta G, the reaction is non-spontaneous, and that would correspond to a negative delta S of the universe. When delta G equals 0, our reaction has reached an equilibrium. Now, just like we had standard conditions for delta H, we also have standard conditions for delta G. This allows us to calculate delta G using the final minus initial idea. So delta G could also be a state function. Under standard conditions then, remember that means we have pure solids, pure liquids, all of our solutions are 1 molar for their concentration, all gases are at 1 atm. For the delta G, we can only do this type of equation at 25 degrees Celsius as well, and we'll come back to this idea. So we can calculate delta G for a reaction by taking delta G of the products minus delta G of the reactants at 25 degrees Celsius under standard conditions. Therefore, we have this little 0 next to our delta G when we're at standard state or standard conditions. Alright, so let's look at finding this delta G value. So based on our equation, to find delta G, we only have to know delta H for the system, delta S for the system, and a particular temperature that we're interested in. So if we look at this first example, if I fill in 75 minus my temperature, I have 410 Celsius, but we remember we need to have Kelvin, so we're going to add to get our new temperature, 683.15 Kelvin. And then we're going to multiply by the delta S. Now here's where we want to look at units. Alright, my delta H was in kilojoules per mole. My delta S is given as joules per mole. So I want to convert this into kilojoules. So remember, to have them in the same equation, they have to be the same units. Alright, so when I calculate then, I get 83.5 kilojoules for my delta G. Since delta G is positive, this indicates that this reaction is non-spontaneous. Now let's examine the sign of delta H and delta S. So delta H here is positive, which means endothermic for the reaction. Positive delta H is endothermic. We have a negative sign for our delta S, which indicates less entropy. Alright, so we have a reaction that is endothermic and has less entropy. Both of those are unfavorable characteristics when we talk about increasing the entropy in the universe. Alright, so our less entropy, of course, is not favorable. And our endothermic means that our surroundings are losing entropy as well. So since I have two unfavorable characteristics, when I put those two together for the same reaction, it indicates that my reaction will never be spontaneous. And if I look at my equation here, and I think about substituting any other temperature, is there any temperature I can put in here that would give me a negative delta G? So if I think about any possible Kelvin temperature, has to be positive. No matter what positive number I put in here, delta G will always be a positive number because I'm subtracting a negative, which means it's only going to get larger. So this one would be never spontaneous. It has two unfavorable characteristics, and based on our equation, no matter what temperature I do this reaction at, it is never going to give me a negative delta G. Alright, now let's switch both the signs. Let's say delta H is negative 75 kilojoules per mole, and let's say delta S is positive 12.4 joules per Kelvin per mole. So now this is exothermic, which is favorable because I'm increasing the entropy of the surroundings, and I have more entropy in my system with a positive delta S. So both of those are favorable, and when I put these into my delta G equation, even at the same temperature we had before, I can see that this is going to give me a negative value. And a negative delta G would indicate spontaneous. And no matter what temperature I put in, I'm going to get a negative delta G because I have a negative number subtracting even a larger number. So it's always going to be negative. So this would be always spontaneous at all temperatures. So we can look at the signs for delta H and delta S to determine whether a reaction would be never spontaneous, or always spontaneous, or perhaps depends on temperature. Alright, so let's look at an example and see if we can figure out if this reaction is going to be spontaneous or not. So in order to use our Gibbs free energy equation, we need to calculate delta H and delta S, and we're going to do that by using the table values. Alright, so we're going to calculate delta H first. Remember, products minus reactants. So we have 105.79 for the Ag plus and negative 167.1 for the chlorine. Then we're going to subtract the negative 127 for the AgCl. So our delta H value ends up being 65.7 kilojoules. So positive value, endothermic. Alright, so let's look at delta S. Same idea, products minus reactants. 73.45 plus 56.6 minus 96.3. Alright, so for delta S, we get 33.75. This is joules per Kelvin. And this would be more entropy. Alright, so we have an endothermic reaction, which is not favorable for the surroundings. We have more entropy for the system, which is favorable. So we have one favorable and one unfavorable characteristic, since they're both positive. So we're going to plug them into delta G to see what we have. So I have 65.7 for delta H. I'm going to subtract 298 Kelvin. And remember to convert your units. So I'm going to make this kilojoules for delta S. Alright, so if I put all these together, I get 55.6 kilojoules for delta G. And this is positive, so this is non-spontaneous at this temperature. And if I think about changing the temperature, is it possible that this reaction will ever be spontaneous? And the answer is yes. If we imagine changing this 298, as this number gets larger, eventually this part of the equation, the T times delta S, will become larger than the delta H, which means it will become negative. So when both the delta H and the delta S are positive, the reaction will become spontaneous as temperature increases, so at higher temperatures. But at 298 for this reaction, it is non-spontaneous. So what does this imply about the solubility of AgCl? So our equation was solid AgCl dissociates into its ions in an aqueous environment. So this is basically talking about dissolving the AgCl in water. But since our delta G value is our positive value, this means that our reaction is non-spontaneous. So it's not going to occur spontaneously at this temperature, which indicates that AgCl is not soluble. It will not readily break down in water. And if you remember your solubility rules, you already knew that. Alright, so we have 4 different categories for reactions based on the sign of delta H and delta S. We've already looked at a couple of them. Our never spontaneous reactions have both unfavorable delta H and delta S. And this is delta H being positive or endothermic, and delta S for the system being negative, indicating less entropy. So if I have a positive delta H and a negative delta S, then my reaction is never spontaneous. No matter what temperature I put my reaction at, it will not occur spontaneously. The opposite of that down here at the bottom, always spontaneous, occurs if I have 2 favorable values, delta H being negative or exothermic, and delta S being positive or an increase in entropy for the system. Both of those are favorable to increase entropy of the universe, so those contribute to a reaction that is always spontaneous. No matter what temperature it's run at, it will be a spontaneous reaction. The other 2 possibilities are temperature dependent. So having one favorable and one unfavorable characteristic means that your spontaneity is temperature dependent. So I can have a favorable delta H, meaning negative, but a negative delta S, which is unfavorable, and that would indicate spontaneous at low temperatures. So as temperature decreases, it becomes spontaneous. Or I can have an unfavorable delta H, which would be positive, endothermic, but a favorable delta S, which is also positive, indicating more entropy. And in this situation, as temperature increases, the reaction becomes more spontaneous. Alright, so on the left is a picture of how the graphs would look for each of these situations. Another way to understand these 4 different conditions is in this table format. So here we have delta H across the top, delta S values along the side. So if delta H is positive, we could have also a positive delta S, which would be temperature dependent. At high temperatures, we would have a spontaneous reaction. Or I can have a positive delta H with a negative delta S, and this is our never spontaneous situation, both unfavorable. Or I can have an exothermic reaction, delta H is negative, with an increase in entropy. This is always spontaneous at any temperature. But an exothermic reaction with a decrease in entropy would be spontaneous at low temperatures. I find the most helpful way to remember it is actually in this format down here. So we have our always spontaneous, our exothermic with our increase in entropy. Our always non-spontaneous is the opposite, so endothermic, decrease in entropy. But for our two temperature dependents, if they're both positive, then it's spontaneous at high temperatures. So I think, positive, positive, up. So positive, positive, high temperature, spontaneous. If they're both negative, then it's spontaneous at low temperatures. So negative, negative, down, negative, negative, low temperatures is where it's spontaneous. However you want to remember it, though, it's important to keep straight those 4 different situations and be able to identify when the reaction is spontaneous, always, never, or depends on the temperature. The Gibbs free energy equation can also be seen as a graphical representation of a straight line. The Gibbs free energy equation fits the equation of a straight line if we consider delta G the y-axis and we consider temperature on the x-axis. So if we graph the change in delta G with the change in temperature, we will get a straight line where our delta H is our y-intercept and our negative delta S is our slope. Alright, so if I rearrange this to fit into y equals mx plus b a little bit better, I would have delta G is equal to negative delta S times T plus delta H. So y equals, and this negative delta S is your M, T is X, delta H is B. Alright, so if we then look at our data, which is graphed for us as a straight line, we can use the equation of the line to find our delta H and delta S values. So in this situation, our delta H is our y-intercept, which would be the negative 208.06, so getting this from the equation, kilojoules. And our delta S is going to be the negative slope of the line. So the slope of the line is positive, but our S is going to be negative. So it's the opposite because we have this negative out front. So we're able to calculate delta H and delta S by looking at the graph. Now if we look at this particular example, both delta H and delta S are negative, so exothermic reaction, which is favorable, but also a decrease in entropy, which is unfavorable. So this is one of those temperature-dependent reactions. Since they're both negative, it would be spontaneous at low temperatures. Alright, and if we look at the graph, we can actually see this as well. The temperature is decreasing to the left. And as we move to the left and temperature decreases, we see that the data goes more and more negative in the delta G direction. So our delta G gets more and more negative at lower temperatures. As temperature goes up, our delta G gets less and less negative and eventually would become positive. So it is more spontaneous at low temperatures. Alright, let's try this again on this graph. We're looking for delta H and delta S. So remember, delta H is going to be our y-intercept, and our delta S is going to be our negative slope. So if we look at our graph, we have the y-intercept on here because it goes to 0. So it looks like our delta H is probably around 253.9 kilojoules. To find our delta S, we're going to calculate the slope, and this is just picking 2 points on the line. So find something that crosses. So I'm going to pick this one that looks like it's on a line. This one looks like it's on a line. And we just do difference in y or difference in x. So 256 minus 254 over 600 minus 100. Alright, so if we calculate our slope, we get 0.004, and this would be kilojoules per Kelvin. But remember, our delta S is going to be the negative slope, so we're going to put a negative in front, negative 0.004 kilojoules per Kelvin. Alright, so in this situation we have a positive delta H, which means endothermic, unfavorable. We have a negative delta S, which means less entropy, unfavorable. So if we have two unfavorable characteristics, then this one's going to be never spontaneous. And if we look at the graph, we can see this as well. As temperature increases toward the right, our reaction is going up in terms of the graph, and we're getting more and more positive delta G values. So as temperature increases, it's just getting more positive delta G or less spontaneous. Since it starts at 0 for our x-axis, we can't go any further to the left. There's no such thing as negative Kelvin. So the reaction was never spontaneous and continues to get less spontaneous as temperature goes up. We can also use Gibbs free energy to look for equilibrium. Equilibrium we're going to look at here in terms of phase change. When we have a substance changing between a solid and a liquid, or a liquid and a gas, we have equilibrium between the two phases. Equilibrium between the solid and the liquid phase, or equilibrium between the liquid and the gas phase. At equilibrium, delta G is 0. Alright, that means neither direction is favored. Neither reaction direction is favored at equilibrium. So if we use our Gibbs free energy equation, by setting delta G equal to 0, we can then solve for the temperature at which that occurs. So for a phase change, that means we can identify the temperature at which the phase change occurs. So for example, if we have liquid water turning to solid water, so this is freezing point for water. We have delta H and delta S, so we're going to fill in our Gibbs free energy equation where we have 0 for delta G, negative 6.012 for delta H, minus, we're going to solve for the temperature, times negative 0.0220, remember converting for units, for delta S. So then when we move this over, move 6.012 to the other side, negative times a negative cancels out, so we get delta H is equal to delta S times T. Then when we divide, we get 273.3 Kelvin. So remember, this is in Kelvin, so 273.3 Kelvin is nearly the same thing as 0 degrees Celsius. So this is the freezing point of water. Alright, so we can calculate the temperature at which we see the phase change. And this can apply to any substance if we know delta H and delta S. Now another way to calculate delta G is by doing our products minus reactants idea. And we said earlier that we could do this only at 25 degrees Celsius. As we've seen in the last few slides, delta G changes dramatically with temperature. So when we look up delta G values on a table, either in your book or online, the delta G values are for a given temperature, and what we see are given at 25 degrees Celsius. So that is the only temperature they are good for. So we can use those values in the table at 25 degrees Celsius to calculate delta G for a reaction. Now, a couple of things to remember. Delta G values are similar to delta H in that any delta G value of an element in its elemental state is going to be 0. Alright, just like delta H. In an equation, if we have a coefficient in front of a compound, we're going to multiply the delta G value by that coefficient. And if we have to flip around a reaction, that changes the sign of delta G. So same kind of rules that we see for delta G are the same as we see for delta H. Alright, so we'll do an example to calculate for delta G. Alright, so we're going to do products minus reactants. 2 times negative 1154.18 plus 3 times 0, because H2 in gas is elemental. Alright, then subtracting the reactants. Aluminum solid, also elemental, so that's 0. Plus 2 times negative 419.2 plus 2 times negative 237.14. Alright, so be very careful with your math. Watch all the negative signs. That's going to be very important. But when you calculate delta G here, I get negative 995.7 kilojoules. Alright, so this reaction would then be spontaneous because delta G is negative. And this only applies to 25 degrees Celsius. Alright, when we look at calculating delta G, since it is products minus reactants, we can also visualize the progression of a reaction based on free energy. So here we have free energy going along the y-axis. Here is the course of our reaction, or the progression from reactants turning into products along the x. If our reactants have more free energy than our products, we see a decrease in the free energy going from reactants to products. This indicates that delta G would be negative. So imagine subtracting a larger number from a smaller number. We would get a negative value. So this is a negative delta G, and we call this exergonic. So if a reaction has a negative delta G, it is exergonic. So it has a negative delta H, we call it exothermic. If it has a negative delta G, we call it exergonic. Right? The opposite over here, still looking at free energy on the y, course of the reaction on the x. If our products have more free energy than our reactants, then we have a positive delta G. So we're subtracting a smaller number from a larger one, so it stays positive. And if that's the case, we call it endergonic. Alright, so a positive delta G is endergonic. A positive delta H would be endothermic. So you can see the relationship there. Another way to think about these, if I imagine having a little marble that's rolling down the hill here, a marble will roll easily downhill, so in the spontaneous direction. But if I have a little marble here, it does not roll uphill very well in a non-spontaneous direction. Alright, so exergonic, we see a downward slope for the spontaneous reaction direction. For endergonic, we see an uphill slide for the non-spontaneous reaction. Now, spontaneous reactions can also do work. Remember when we talked about our energy is equal to our heat plus our work? We can look at work based on delta G values. Alright, so if we have a spontaneous reaction and delta G is negative, that means our reaction can do work. So if delta G is negative, the reaction does work. If delta G is positive, no work is done by the reaction. Alright? Delta G is also a measure of how much work can be done by the reaction. The more negative the delta G, the more work can be done. Positive delta G values mean the reaction can do no work, but the value indicates how much work must be done to the system in order to get the reaction to actually work. Alright, so we're going to try a calculation with this. How much work can 8 grams of sulfur do in the reaction? Alright, so if I start with 8 grams of my sulfur, I'm going to relate it to my delta G. Now I'm going to use my delta H and delta S down here to calculate what my delta G value is. Alright, so I'm going to fill in my delta H at 298 Kelvin, and my delta S, remember converting for units, and then I can calculate delta G, and I get negative 538.6 kilojoules. So it's negative, it's a spontaneous reaction, it can do work. So we're going to relate our sulfur to our delta G. And this is very similar to how we related our delta H value when we were looking for kilojoules or Q value for heat. So the first thing we're going to do is convert this into moles. So 32 grams per 1 mole of sulfur. That's from the periodic table. And then I'm going to use my delta G value. Negative 538.6 kilojoules of work per 1 mole of sulfur, because the coefficient is 1. And this will allow me to calculate kilojoules of work that are left. So I get negative 134.6 kilojoules of work. So instead of this being heat, this time it's work, measured based on delta G. So the negative indicates it's spontaneous, and this is the work that the reaction can do. And the 134.6 is based on starting with 8 grams of sulfur. If I have more grams of sulfur, the reaction can do more work. Alright, so to summarize this part, spontaneous reactions can do work. That means they have a negative delta G. They also have a negative W for the work. The delta G value tells you how much work can be done by the reaction based on how much starting material you have. It's never exactly equal to delta G because there's always some of the work that is lost as heat, because no system is perfect. Non-spontaneous reactions, delta G is positive, cannot do work at all. You have a positive W, indicating that the surroundings must do work on the system. And again, the value of delta G can tell you how much work must be done on the system, but it's not perfect because you will lose some as heat. Once delta G equals 0, the reaction can no longer do any work because it reaches an equilibrium. Now, one last idea with this idea of work is how can we get a non-spontaneous reaction to occur? In order to get a non-spontaneous reaction to occur, we have to attach it to a power source, or we can couple it to a spontaneous reaction that does work. So in this example, the reaction that we're interested in is copper oxide breaking down into solid copper and O2 gas. This is beneficial because copper is worth a great deal of money right now, so if we can separate copper from the copper oxide, it can turn a profit. But you'll notice non-spontaneous reaction. So this is not going to break apart by itself. So we have to think about how we can make this reaction occur. Using the second equation, carbon in the presence of O2 turns into carbon monoxide. And you can tell from the delta G that this is a spontaneous reaction. So if I mix carbon with my copper oxide, the carbon can take any oxygen that might be present and turn it into carbon monoxide. Removing the oxygen then drives this first reaction forward. If we think of it as Hess's law and putting the two reactions together, so adding these two equations together, so the O2s will cancel out, we get this equation. Carbon in the presence of our copper oxide produces the copper that we want, and carbon monoxide is a byproduct. Adding our two delta G values together gives us a slightly spontaneous reaction when these two reactions are coupled together. So we're using one spontaneous reaction to drive the non-spontaneous one.